All right, let's jump right into this explainer. Today, we're going to demystify the modern soil monitoring ecosystem. We'll literally be tracing the journey of a single piece of data, starting deep in the dirt and traveling all the way to a smartphone screen. If you're an undergrad studying agronomy, environmental science, or engineering, getting a solid grip on this system is absolutely foundational for your future career. So let's get into it.
Think about this. How exactly does a farmer know a plant is thirsty before it actually wilts? Well, that biological question drives our entire journey today. How do we spot what's happening underground before a crop shows visible signs of stress? The secret lies in understanding the complete Internet of Things, or IoT, architecture. It's not just a single fancy tool. It's a whole connected web of technologies working together seamlessly.
Here is our agenda for today. First, welcome to precision agriculture. Second, how soil sensors work. Third, sensor languages and protocols. Fourth, wireless networks and LoRaWAN. And finally, number 5, smart apps and decisions.
Starting off with Section 1, welcome to precision agriculture, framing the big picture. We're going to follow the physical journey of a data point step by step. It starts the moment water is measured in the soil, moves to the protocol the sensor uses to transmit that data, then hits the wireless network beaming it through the air, and finally lands in the cloud where it's processed into something we can actually read. Moving right along to Section 2, how soil sensors work, the physical layer. Now, let's talk hardware. As students learning about different agricultural setups, you already know that not all soil is the same, right? Take the GS3 sensor, for example. It was specifically engineered with these super slim stainless steel needles so it can easily slide into highly porous greenhouse substrates, stuff like peat, rock wool, or perlite. It operates in a really condensed volume, which makes it absolutely perfect for the unique, controlled conditions of potting containers. But if you're dealing with tougher outdoor environments, you're going to need something way more rugged. That's where sensors like the Teros 12 come in. They use sharpened needles designed to cleanly slice through compacted mineral soil without messing up its natural density. And here's the crucial part for your field research. It has a massive 1,010 milliliter volume of influence. That's basically sensing an entire liter of soil. By covering such a huge area, it averages out local structural anomalies, giving you incredibly reliable data. So how do they actually measure the water? To simplify the science just a bit, these sensors don't drink the water. Instead, they measure dielectric permittivity. Think of it like a highly targeted ultra-low power radio broadcast right into the dirt. They send a 70 megahertz frequency wave to the prongs to detect water. And using that specific 70 megahertz frequency is pretty brilliant because it perfectly isolates the reading, meaning you don't get distracting interference from the soil's natural salinity or texture.
The big takeaway here is that a modern digital tool like the Teros 12 is a total multi-parameter powerhouse. Compared to those older, simple analog sensors that just gave you a basic voltage reading for moisture, this single tool measures volumetric water content, temperature, and electrical conductivity, all at the exact same time.
Next up, Section 3, Sensor Languages and Protocols, the Data Link Layer.
Okay, so once the hardware takes a measurement, it has to talk to a data logger. This is a super common trap for new engineers and agronomists. If your sensor speaks one protocol and your controller speaks another, they literally cannot communicate. It really doesn't matter how accurate your sensor is if the controller has no idea what it's saying. Let's look at the two main languages you'll encounter. First up is SDI 12. This is basically the scientific standard for remote environmental monitoring. Why? Well, it operates on a ridiculously low power budget, which is a total lifesaver for solar or battery-operated field stations. Plus, sensors from companies like Meter Group have a special low impedance design that lets you daisy chain up to 62 uniquely addressed sensors on just one single data wire. Pretty cool, right? On the flip side, we've got Modbus RS485, which is the industrial standard. You definitely go with this if you're setting up a network near heavy irrigation pumps or noisy electric motors. Modbus uses differential signaling, which gives it massive immunity to electrical noise. And the range? It can send data over incredible distances, up to 1,200 meters, without the signal degrading at all. That's over a kilometer.
All right, Section 4, Wireless Networks and LoRaWAN, the network layer. Out in a massive agricultural field, your standard Wi-Fi just isn't going to reach, and cellular connections will absolutely chew through your batteries. Enter LoRaWAN, which stands for Low Power Wide Area Network. It acts as the wireless bridge for our IoT architecture, beaming small data packets to a gateway up to 15 kilometers away in line-of-sight conditions. To put that into perspective, that's like sending data across an entire city, all while running on a tiny battery budget using sub-gigahertz frequencies.
And finally, Section 5, Smart Apps and Decisions, the application layer.
The whole point of this massive data journey is turning raw electrical voltages into dynamic dashboards that farmers, researchers, and land planners can actually use. Let's be real, raw numbers mean absolutely nothing if you can't interpret them quickly to save a dying crop or optimize a watering schedule.
A perfect example of this is the LandPKS app. This is where basic manual observations meet advanced algorithms. The app actually lets users identify soil color and texture right in the field using just their smartphone camera and a reference card. It queries global cloud databases to identify the soil profile. Then, when you combine that on-site data with the real-time sensor readings we talked about, the system calculates a dynamic metric called plant available water, or PAW. It tells you exactly how much of that moisture the plant can actually drink. And the best part? You can log all this data fully offline when you're out of cell range.
So why does all of this matter? By bringing all these layers together, we achieved closed-loop precision irrigation. We avoid underwatering, which stresses the crops, and we prevent overwatering, which causes harmful nutrient leaching. Beyond just farming, this technology is a real game changer because it directly saves resources and protects vulnerable wildlife habitats from the brutal effects of drought. The golden rule to remember here is this: accuracy is about more than just the sensor. It's about optimizing the accuracy of the whole data set. A flawless, top-of-the-line sensor is absolutely useless if the communication protocol fails, the network drops, or the software misinterprets the soil type. True accuracy requires the entire ecosystem working in harmony. So, as you step into your future careers, I want to leave you with this question: how will you use this complete IoT ecosystem to reshape our landscapes? You now understand the basic building blocks, from the dirt to the cloud. As the next generation of problem solvers, the impact you can have by mastering these precision agriculture tools is literally limitless. Thanks for joining me on this explainer, and keep learning.